Philip, Martin, you take the stage.
There we go. Hey everyone. So welcome to our next talk, Variable Rate Compute Shaders in Doom: The Dark Ages. My name is Philip Hammer, Principal Engine Programmer at id Software. I'm doing this together with Martin Fuller, Principal Engineer at Xbox ATG. I'll briefly talk about the context and motivation, again, why we need variable rate shading in Doom. And I'll also explain a few of the basic techniques and some of the implementation details. And Martin will take over roughly in the middle of the talk to deep dive into the details of the techniques and many of the obstacles and problems we had to overcome. And it's also a story about a great collaboration between id and ATG and why it's sometimes great to work in a larger corporation. So our goal in Doom was, again, we heard this 3 times today, I think, to ship a game with stable 60 FPS across all our target platforms, no matter what. And at launch, those were the Xbox Series X and S, PlayStation 5, and basically all ray tracing capable PCs. And recently, we also shipped the game for the Rogue Xbox LIX at launch, also in 60 FPS. Performance is key for us and the first-class citizen during development. However, this time, again, we had much larger maps, much more content on screen, much higher scene fidelity and things like that. And at some point, you really need to balance pixel quality, resolution, and performance. And in that sense, we really only want to compute those expensive pixels when necessary. So let's continue with a bit of history to set the ground. Doom Eternal, our previous game, was originally released on Xbox One and PS4 level hardware in early 2020. And when we ported Doom Eternal to the Gen 9 consoles in 2022 with ray traced reflections and a 120 Hz mode, etc., we also added VRCS support. And 2 of our main passes, opaque and transparent rendering, they were rasterized and they were benefiting hugely from hardware VRS. And those passes is where we evaluate all the materials, run the lighting, blend decals, etc. So basically outputting the final color. And we found that VRS was a great fit for that kind of pipeline, our forward rendering. And expensive pixels were calculated in the forward pixel shaders, and VRS helped us just to minimize the invocation count. And this is also where the first collaboration with Martin first kicked off. So he invited me and Chris from the coalition to contribute to one of his talks on YouTube in the middle of the pandemic. So the talk is in the slides, so go watch it. I think it's still valid information. And this is a screenshot from that presentation showing some really nice performance gains in Doom Eternal. So what changed from ITTEC 7 to ITTEC 8? I mean, this is a very, very simplified diagram, but the main thing was that we replaced our main opaque pass with a deferred texturing and a deferred lighting solution, the things that we talked about this morning. So note that this formerly rasterized pass is now changed to a series of compute shaders, and only transparent rendering remained forward. And yeah, this forward transparent is pretty much what we had since Doom Eternal. And by the way, replacing the opaque pipeline with a visibility buffer and deferred rendering approach, that was part of our talk earlier. And little recap, the main idea was to minimize the amount of helper pixels. And we just want to do the heavy lighting calculations only on those pixels that are actually visible and not on the helper pixels. And the remaining raster work that's still left, which is like the depth and visibility buffer rendering and shadows, they are lightweight enough that we can afford the helper pixels. Yes. So we've seen great results with that approach first. So we seen a solid 2 to 3 milliseconds win overall on GPU frame time, and hooray, we're done, right? But if you know that meme, you can imagine it's not the end of the story. So for quite a while, we were happy with how much our new renderer performed compared to the F+ renderer. And we optimized everything with VRS disabled because we wanted to have a fair comparison. And we knew that we needed to address the missing VRS at the new pipeline at some point. But then, when we did it, the real-world performance was, well, if we enable VRS on the visibility buffer approach, we again lose all our head start. So yeah, we needed to address this somehow. Now what? Well, this is what the talk is about. Enough history, I guess. VRCS to the rescue. So we early gravitated towards a technique called variable rate compute shaders, but we didn't find any shipped games at the moment when we started looking into it. So it was a bit of uncharted territory. Martin did a great talk from 2022 together with an ATG research sample. And yeah, we looked into that. And on the good side, we managed to get the technique implemented in around 2 weeks. And we've seen very, very promising results. However, a proof of concept is very rarely ready for production. So after the initial excitement, we found many, many edge cases where VRCS just didn't work as intended. And we've also seen quality issues. So what happened then? We had a little email conversation with Martin. He gave us some tips, and then he said, hey, I have some time. I'm coming over to the Frankfurt office. And stayed there for around 8 days, I guess. And yeah, we shipped VRCS on Doom together. So what's the purpose of VRCS? In short, in one sentence, it's basically saving performance by retiring entire compute waves early. And we reduced the number of unique pixel calculations based on the shading rate. And those uniquely calculated pixels, they might copy their result to their neighbors, so we don't get holes in it. So far, it's the similar approach as with hardware VRS. And we apply VRCS to full-screen compute passes that have expensive or ALU-heavy pixels. And lightweight pixels, such as the visibility and shadow map generation, they do not benefit much from VRCS, so they just don't apply it, and they just don't use it. So again, this diagram, we use VRCS for those following passes. Currently in ITTech, we plan to use it on more. First and foremost, deferred texturing, which contains all our material evaluation and blending and generates the base G-buffer, the things that we talked about this morning. Then the deferred G-buffer update, which blends geodecals, projected decals, triplanar blood, and environment wetness and rain on top of the base G-buffer. Then deferred lighting, which runs the lighting calculations and checks for shadow map occlusion and outputs the final lighting. Those passes had it enabled VRCS. Initially, we also used this on our deferred composite pass, which is used to blend all sorts of additional things on top of the final scene, for example, global illumination, resolving environment probes, blending fog reflections on top of the final color. However, the benefit wasn't that high. I think it was like 200 microseconds that we saved there. But this pass particularly is upscaling a lot of effects with temporal noise dithering. So we have small fog or GI textures or reflections that get upscaled and dithered with noise, and we hope that the noise will resolve after TAA. But now when we used VRCS on those noisy passes, Martin will go more into detail, we've seen horrible artifacts, and we couldn't really fix them in time, so we disabled it for that pass at all. So it was not catastrophic. So let's get a bit into the trenches and go over how the VRCS actually works. So in general, I'm referring to Martin's talk from 2022, but just giving a small summary here. So we essentially create 2 shading rate images, and both are 8 bits per pixel, and based on the full screen luminance from the last frame. And the first one you see is the hardware VRS SRI shading rate image, which has a tile size of 8 by 8 pixels on Xbox, varying tile sizes on PC. And the second one, which is a 2 by 2 SRI on all platforms, and we use that for the software VRS implementation. And to generate those, we analyzed the Luma image that you see here for gradients to determine what the minimum shading rate is needed for that tile. So we are looking for low contrast or low frequency quads, where all the 4 pixels in one quad are very similar. So we can reduce them potentially to 1 uniquely calculated pixel for the whole quad and then copy the rest to the neighbors. So we also have similarity metrics that are configurable. For example, VRCS tolerance, that's basically just a filter tolerance, how much error we essentially tolerate. So here's the mapping between shading rate and the quad configuration. So the green pixels on the right column depict so-called primary pixels. And that means they run a unique shading calculations, and it means it just runs the full shader. And the blue pixels, however, they are duplicate pixels, and it means they receive a copy of their respective neighboring primary pixels. And the tile shading rate in combination with the primitive coverage determines the uniquely calculated pixels, and is defined like this. Like the 1-by-1 shading rate is easy. It's basically every pixel in the quad is uniquely calculated, so we have no shading rate, no coarse shading. Then the 2-by-1 shading rate, which means 2 pixels are uniquely calculated and copied to their respective neighbors horizontally. The 1-by-2 is the same, but copied vertically. And note that those half-raised pixels are arranged in a checkerboard pattern that we alternate every frame. Actually, the shader program that runs on the primary pixel is actually also the one that copies to the duplicate pixels, but more on that later. In full screen, we can visualize that whole process and just see the primary and duplicate pixels. And it's the same color coding as in the diagram, but additionally highlighting the full 1-by-1 and full 2-by-2 rate tiles in yellow and in pink. And when zooming in, you can actually see it. You can spot the checkerboard setup that I just talked about, like where 1 or 2 primary pixels are in green, and then a corresponding 2 to 3 duplicate pixels in blue. So far, so easy. So we have a set of pixels that run the full shader and another set of duplicates that run early outs in the shader invocation. So one invocation is expensive and the other one is cheap. And the more cheap invocations we get, the more performance, correct? Unfortunately, it's not 100% how the modern GPUs work. So if we compute primary and duplicate pixels mixed within the same wave, we gain nothing at all. So we pay the cost for as if all the pixels were primary. So in order to gain an advantage, we have to group primary and duplicate pixels together. And the goal here is to have full waves of duplicate pixels that can early out entirely and recycled by the command processor as soon as possible. In order to group primary and secondary pixels, we have to schedule them in a different way by remapping their coordinates. And to pull this off, we have to add another pre-processing step, which is a compute shader that we run again. So what we do is we segment the whole screen into 16 by 16 pixel tiles, where each tile can be represented by 8 wave32s with an 8 by 4 thread group layout. And one interesting property here is that all the threads are tile local, so we're still getting scalar light loads from our clustered binning. And for each of those tiles, we store the primary pixel count. And additionally, we have to store some additional data per pixel, which is 8 bits for a tile relative X and Y offset, which means 4 bits per dimension. That's why the 16 by 16 tile size comes from. And 3 bits copy commands that just indicate where to copy the primary pixel's value to. Is it vertically, horizontally, diagonally, or all 3 of it? So and this is how shading rate and coordinate remapping are related to each other. So on the left, we see an example with 4 different shading rate tiles, and each tile relates to a pixel quad. So this illustration, we're dealing with 16 pixels in total. And in the middle, we see how the shading rate tiles unfold into primary and duplicate pixels if you would just use the global invocation ID of the compute shader. And if we reschedule this work, then we see something like on the right. And this is basically our goal. So we need to remap the coordinates of those pixels to achieve basically a wave coherence. Again, this is like really our 16 by 16 tile. It's covered by 256 pixels, computed by 8 wave32s. And in this example, we just chosen arbitrarily 132 pixels. Did anyone count it? And 124 duplicate pixels, just arbitrarily chosen. And this diagram shows the work scheduled in screen coordinates as they would be dispatched without any remapping. And what happened? Can I go back? How can I go back? Thank you. Yeah, that's it. Yeah. So if we now remap the threads to process the primary pixels in batch, we get, in that case, 4 primary pixels, 4 full waves with primary pixels, and 1 partial wave, which is still processed at full cost despite only running 4 primary pixels. And we get additionally 3 full waves of duplicate pixels. And this is where we actually gain performance, since they will be very cheap. So they will early out fast, since all the threads uniformly hit the early out branch, and the CP can use the wave for other work. So one more detail here. We can leverage the fact that we need to save at least 1 wave in order to get a win. And if this tile has more than 224 primary pixels, that is 256 minus 32 from the wave size, we have to execute a 1-by-1 shading rate for the whole tile anyway. So we don't have to store and remap the coordinates. Therefore, we only have to allocate memory to store coordinates for 224 entries per tile and not 256. Minor detail. So how do we implement this? Again, we follow approach from the original idea. So once everything is set up, we have a buffer with the coordinate remaps and the copy bits. And all we have to do is adding a prefix and a postfix function to the shader where we want to use the VRCS. And the prefix function remaps the original pixel location and retrieves a UN32 that is called in that code snippet VRCS data, which contains the bit-packed tile relative offsets and the copy bits. And after that, we run the shader as usual. No changes are needed. But mind, the pixel shader location is now different. So a problem is that things like quad shuffle subgroup operations won't work as intended, since you don't get the neighbor that you actually expect. So you may want to find alternatives. And at the end of the shader, we call VRCS postfix that writes the output value and does the copies to the duplicate pixels. The prefix function essentially computes the tile index to query the primary pixel count, which is in another buffer, VRCS count buffer, and the VRCS data, which is in the VRCS coords buffer. And the VRCS data is used to remap the original pixel coordinate, that is just the tile coordinate plus the pre-computed tile relative offset. And the data is also returned, so we can retrieve the copy commands later in the postfix. The postfix function is rather trivial, so it really just stores out the output value that we computed in the pixel to the target image UAV. This is basically the primary pixel. And then it checks what kind of copy is needed, which is either horizontal, vertical, or diagonal, or all 3 of them together. So based on the original shading rate, and then we just make the copy and store it out to a different set of coordinates. So a typical scenario is full-screen compute passes, for example, those that we use for our deferred lighting passes. And we dispatch as many thread groups as we need to fill the screen, as usual, actually. But we want to cache in on the early out waves, so that are full waves with only early out threads. So usually we have 1 partial wave per 16 by 16 tile, and that means in average 1/8 of all the waves for full screen dispatch are partial waves. That is for 1440p resolution, 14,400 partial wave 32s. It's not great, but also not terrible. It's no way around that scenario. We just have to deal with it if we use this dispatch scheme that I just described now. Minor nitpick pointed out by Martin. It's not correct. We don't always have 1/8 of partial waves. Sometimes we just hit a full wave. So then we don't have any partial waves. Anyway. We have a better opportunity, actually, with our deferred texturing dispatch setup. If you remember the first talk, the deferred texturing does not operate on full screen, but has like a list of pixel commands. And since we have here a compact list of pixel commands, and they will be dispatched in a later step, we can apply like just a different approach to it. We don't even need tiles for it. So we also don't do any lighting or decals here, so we don't really rely on scalar light loads there, which might be disadvantage, but not in our case. And the idea here is that while we count the pixels that we want to render later, we only add the primary pixels when we collect the pixels. And this way, we never ever dispatch any early out pixels, the duplicates, in the first place. So this is even more efficient. And yeah, since this setup, the pixels are not organized in this 16 by 16 tile setup, so we can reduce the amount of partial waves to a maximum of 1 partial wave per screen, which is even more efficient. We still have some waste from the pixel command generation because you remember the padding pixels that we need to fill the full wave. But this is unrelated to VRCS and in general also not a big problem. The future, we're not done here, so we already have a lot of ideas how to make this more efficient. So I've seen the VRCS being most effective in our pixel dispatch commands and deferred texturing, and we essentially eliminate partial waves and always launch fewer compute threads in the first place. So consequently, we were toying with the idea of using that dispatch scheme also for other deferred stages, such as deferred lighting, a gbuffer update, etc. It would be a bigger change from what we have now, so we didn't explore this any further, but this is definitely something for the future. Another idea was just to run texturing, lighting, gbuffer update in one shader again. This would be a similar setup like F+, but in compute. We tried this, but it was a little bit slower than what we have now, and we ran out of time, so we didn't explore it any further, at least not for the launch, but we will definitely look into that. Again, putting too many features into the same shader gives us VGPR problems and occupancy issues, and so forth. And now I welcome Martin to the stage. Thank you.
Thank you, Philip. Okay, so when I onboarded to work on doing with Philip and the gang over at Frankfurt, Philip already had it running. He was seeing very good wins of 1 to 2 milliseconds, but the quality wasn't quite there. And I did 2 weeks near enough at Frankfurt, and then 3 weeks before CodeLock, working remotely to see firstly whether we could get the quality that we needed, and then to get the performance back to where it already was. So the first issue we had was that there was a pixel offset problem happening, and this was happening particularly with 2x2 rate. And the issue is that what we'd implemented is not quite how hardware VRS works, which had tackled this. So with hardware VRS, the pixel in shader is invoked in the center of the coarse pixel, and then it is copied to the covered pixels. And this avoids any kind of offset in the image. In VRCS, this is not the case. We were just picking one pixel, running the compute shader at that point, and then copying. So this produced a kind of noticeable shift in part of the image. Kind of odd, well, very odd. So first thing I thought of was, well, we could just modify the compute shaders to do exactly the same as hardware VRS does. That would have been slightly invasive. We had added the prefix, or Philip had added the prefix to the postfix function, but other than that, we hadn't changed the shaders in any way, shape, or form. So we could have gone through all the shaders, found all the texture samples, offsetted the sampling location. There wasn't a lot of enthusiasm for doing that because we're adding a cost if it's 1x1 rate. So we could come back to that in future, but the first thing I tried instead was rotating which pixel is the primary pixel per frame. So for the half rates, this is easy. It's flipping the checkerboard, the effective checkerboard you get. The problem again was the 2x2 rate. It would take 4 frames to go through the cycle. This was too slow, even at 60 hertz. It didn't produce a stable image. So what I did, or what I ended up shipping was flipping between the top left and the bottom right pixel, unless we had only 3 covered pixels, in which case we have an L shape, and we just ping pong back and forth on the L. That made things better, but it wasn't really a great fix. So the next thing I did was to add a deblocker, and I was straight to Activision's paper from McCall Drobot, Very simple implementation. We knocked this up in about an hour, so there was no code sharing. It was quicker just to write it. Very simply, if it's 2x1 rate, then we're doing an average horizontally. If it's 1x2, we're doing an average vertically, and if it's 2x2, we're doing the average of 4 surrounding pixels diagonally. This is what that looks like. This is a screenshot from Xbox Series S at a very low resolution here, 736p. In fact, Series S was, we really pushed variable rate compute shaders to their limit. Even this specular highlight is not generating 1x1 rate, which is quite remarkable that we were able to get away with that. But that is entirely, I think, down to the deblocker. So you can see here the effect of the deblocker is to clean that up quite nicely, and then by the time we've run post-processing and TAA, you would never know. So there was a quality issue here, which is that I wasn't respecting coverage. So when we're doing this deblock, it's spilling pixels over the edge of a surface. I did try respecting coverage, and that, in fact, it slowed it down, and that has a different problem. And the problem is that sometimes we want to deblock over triangle edges. So if you imagine this skull is tessellated with lots of triangles, as normal, then we need the deblock to work over those edges. So that correctly sorts out the specular issue. So what did I do about it? Well, absolutely nothing. It turns out, again, it gets tidied up in post, and we were really against the clock. So, yeah, we could fix that with a def test in future. So the deblocker as well, we're trying to keep things as fast as possible. It's a bandwidth-limited shader. It's also writing out luminance for the shading rate image. And to keep it fast, we use the same input and output UAV. This is technically wrong, but it halves our bandwidth. And technically we have a race condition, but nobody could see anything, so we ignored it completely. So there we go. The deblocker was awesome. It worked brilliantly. It fixed this kind of half-pixel slide in the image. It allowed us to be massively more aggressive on shading rate, as you've seen with that skull. And Digital Foundry called us out. Sad times. And it just so happened that it was like, it's weird. This is like in the far distance. What's going on? We can see the blockiness right in the far distance. And it turned out that we'd accidentally turned off the deblocker for lightly fogged screen tiles. So it just wasn't running. And they were like, look, we can see this. So one of the very first patches after the game shipped, we turned the deblocker back on for fog tiles, and all was well with the world. Except noise. I hate noise with a passion. So, and it turns out that IDTech 8 uses rather a lot of rotating blue noise. And things like raindrops were not a problem for VRCS. It was like it's a fairly random event, but it's not per frame random. So we could cope with raindrops. But where we're using noise to do things like blend between shadow cascades, that was a real problem, because there would be a single pixel fizz that TAA would largely clear up. But when you blow that up to 2x2 rates, then TAA doesn't fix it quite so well. So this was a real problem for 2x2 rates, but the key observation was that it wasn't really an issue for the half rates. We were getting away with it, 1x2 and 2x1. So the solution here was calculate the shading rate. If we have a 2x2 tile, then calculate the shading rate again with reduced tolerances, but this time don't let it promote to 1x1 rate. So a 2x2 could promote to a half rate in this second round of computing the shading rate. So what does that look like? We have this scene here where we're doing significantly more half-rate shading, which you can see by the increase in the number of green primary pixels. So that's happening a lot in the midground, the foreground, and the trees in the background. The pillar on the left and the mountains have managed to resist. But you can see this cost 600 microseconds, so this was an expensive fix for noise. It did help with normals as well for SSR, so because we are generating more difference in the G-buffer normals, and reflections are particularly sensitive to the G-buffer normal. So we just lost a load of our performance, sad times. What can we do to try and get back to that 1 to 2 millisecond win? So the first thing we did was fail to load the images off the hard disk. Oh. Well, the top 2 images are the most relevant. So what we have here is we've tied the shading rate to the dynamic resolution scale. So as we're going to a lower resolution, we are also at the same time reducing the shading rates, so we get less primary pixels. And at 75% resolution, we start doing a foveated reduction as well, so we start reducing the shading rate more at the edges of the screen. Well, that's another image that's, no. Well, I'm very sorry about the lack of images. So what is variable rate shading worth? And the answer is it really depends on the resolution you're running at, because we've tied it here. We set about 85% resolution. We said that's the quality we're aiming for. That's our ideal quality. And then I think possibly the very last commit that went in was somebody said, well, if it's at better than 85% resolution, you might as well let it overshoot and run at a higher quality than we think it even needs to. So, and it still can't load that image. So we got some different savings, and it depends very much at what resolution you're running. So at 1440p, which is the maximum resolution on Xbox Series X, we have the quality overshoot is active by quite some margin, and we're only saving around a millisecond. 85% resolution, we're starting to get concerned. We want the biggest saving we can get, really. So we've got a full 2 millisecond win for the same scene. And then as the resolution reduces down towards 1080p or lower, we're now struggling. VRCS is struggling to find duplicate pixels. Triangles are getting smaller, so the win is reducing. Inevitably, this always happens. Something else I did to try and bring back some more performance was this observation that sometimes we had transparencies that were occluding or partially occluding solid geometry and actually boosting the shading rate on the solid geometry behind. So to fix that, I actually again calculated shading rate twice. I'm already doing it twice, that's 4 times. But in this case, we stored out the luminescence twice, so before and after transparency rendering. We calculate the shading rate from both lumas, and then we just take the minimum shading rate. And you can see here, because it has managed to load some pictures, the reduction in shading rate in the VRCS buffer, specifically behind this flag, and then the reduction in primary pixels in the VRCS debug. Another thing I went after for performance was the overshading of triangle edges. So if we have a completely flat floor, which we have in this image, and it's tessellated, because that's what artists do, then we have this additional shading on the outline of the silhouette of each triangle. Just in case you can't see that too well on the projector, is a zoomed-in version. So I wanted to get rid of this additional shading that was just completely unnecessary. So this is quite simply a dot product and a depth test, saying, are these 2 triangles on the same plane? And the shading rate is low, so therefore I can share the shading. I didn't have the face normal, so this was a drawback to this particular optimization. So again, with no time, I recreated the face normal by doing a little search in group shared memory. This is a terrible algorithm. Don't do it. Don't copy that. But it did save around 150 microseconds. I will come back to better ways of doing that. Some other performance wins, some VRS implementations, they just set the border tiles on the safe area of the television to 2x2 rate. That didn't work in our case because the noise issue would show up, you could see it. But we did slightly reduce the shading rate on the border tiles. Another optimization was this idea of a tile having a state, having various flags that were either stored or derived. So if the tile was entirely 1x1 rate, then we don't need to load coordinates from the buffer. We can just use dispatch thread ID. If it's entirely 2x2 rate, we can programmatically decide where the locations are that we're going to shade. So again, we don't need to load from the buffer. Quite often, deferred passes don't care about sky, so we can have an early out on sky. And as Philip mentioned, originally in the composite pass, we were running VRCS, and we wanted to know whether that tile was fogged because we had a problem with fog. So if it was fogged, we would run 1x1 rate. If it wasn't fogged, we'd run whatever else was specified on the tile. Computing whether a tile was fogged or not was quite expensive. Fog volumes are 3D, they're expensive to sample. We were essentially doing this at half resolution because we were running, when we're building the VRCS buffers, we were running one thread for every 2x2 tile, 2x2 pixels. So tasking that one thread with sampling the fog volume meant we were sampling the fog volume at half resolution. But yeah, it was a nice optimization that then got taken out. Results. So the end result of that was that we managed to improve the quality and we managed to actually retain the performance with the additional optimizations. Interestingly, the best case here is not that much better than the average case. So the best case is you put your head in the wall and there's not much to look at. And we're saving 2.1 milliseconds at 85% resolution. There's almost a millisecond coming from deferred texturing. There's 400 microseconds coming from the deferred G-buffer update, 800 microseconds from deferred lighting. In the average case, we're saving 1.8 milliseconds, very respectable. And again, most of this is coming from the deferred texturing and deferred lighting, where we're chopping a third off the time. The worst case, this was the area that we spent a lot of time profiling. We knew it was the first siege level. We knew this was a problem case. Digital Foundry found it as well. It's largely due to foliage. There's an awful lot of grass blades there. I hope you can see it on the projector. But even at 85% resolution, again, we're getting a 600 microsecond win. And this wasn't a particularly typical scene for the entire game. So, yeah, we got some excellent performance wins across all the consoles. We were frequently saving a third of the time on the deferred texturing and the deferred lighting passes. It does depend on the content, and it does depend where you are on the DRS scale. After shipping on console, I mean, this was so down to the wire. Unfortunately, it didn't ship on PC day one, but Philip got it working shortly after shipping. And on the ROG Xbox Ally X, we were seeing similar gains with the TAA simple setup that we had on console. Unfortunately, if you were running FSR, the cost of FSR on that machine is so high, it pushes down the internal resolution, and then variable rate compute shaders are struggling to find duplicate pixels. We have small triangle problems, so the win was not nearly so good in that case. So we shipped it, but there's a lot more we could do. There's a lot we could fix. So I want to spend some time to share thoughts there. The first one is we could use this to accelerate ray tracing in a big way, and there is a huge potential here. So there are an awful lot of ray trace passes where the rays originate in the visible frustum, and we could do just the normal thing with VRCS. We could just fire all those rays from a primary pixel, copy the results to the duplicate pixels, or if you're lucky enough to own a GPU that can actually fire more than one ray per pixel, you could perhaps reduce the number of rays fired per pixel based on the number of duplicates, because you're, by definition, saying this is not a very interesting area of the image. Reducing the internal shading of triangle edges. So, as I mentioned, I had that horrible algorithm for trying to reconstruct a face normal. We could store the face normal. This is how little time we actually had to make this work. We could recreate it because we are processing all the triangle data when we're building the barycentric buffer. So you could grab it then. We could potentially use the tangent frame, but I think we can do even better than that. And if we look at this image here, again, hopefully it's showing up okay on the projector. There's a lot of extra shading going on. I mean, the shading rate image is saying there's some interesting stuff going on the left-hand side of a face because of the lighting on the chin, on the eyebrow, the gold leaf around her neck, this device she's holding. But actually, if you can see it, and I'll zoom in case you can't, there is a lot of additional shading that's going on in the interior of the skin, the interior of the cloak. We just don't need that. That's purely down to the fact that we're using triangle ID. The silhouette of the object there has got a nice high shading rate anyway, and around the texture detail of this device, that's all being picked out. So the solution is we've written a lovely renderer using triangle ID, and now we want to stop using it. So what we actually care about is continuous surfaces, like the real world. So we care about the silhouette of a surface. And this is analogous to MSAA, where you're getting a win on the silhouette of a surface, but you're also paying for the MSAA resolve internally, and you can't see any benefit. This is exactly the same problem. So we care about the silhouette, we care about the surface self-overlapping, which we can detect with a depth check, and we care where the shading rate image tells us to care. And this would significantly reduce the number of primary pixels, and we, not just cloth and skin, but foliage as well. So it's really a tooling problem. How do we identify continuous surfaces? And if we had that, we don't need a visibility buffer. You could lay down the surface ID with the G buffer, for example. Something else we could have done with a bit more time, there's about 10% of the frame time is given over to SSDO. You saw the visual benefits in the earlier talk. This is computed at half res, about 1.3 milliseconds to compute it, about 300 microseconds to blur it. So to run VRCS here, we need a few things that we didn't have. So we needed a half-rate shading rate image. That's easy. We can just output it from the shading rate shader. Very simple. We would need to create a half-res coordinate buffer. We can hide that cost on async compute. We probably don't need a deblocker because this thing's getting heavily blurred. The win, if you're doing this with triangles, all your triangles are now a quarter of the number of pixels. So the triangle edge problem becomes more significant at half resolution. So my prediction is we would get a much better win if we were working with surface ID rather than triangle ID. I don't believe it. How strange. Right, anyway. So on the left-hand image, you can see that the extra half rate of the extra half-rate shading we injected to combat noise has significantly increased the shading rate of the grass, and also the kind of surface on the left of the grass there. And we've got these full-rate tiles. In the image that you can't see, there is far less of those yellow tiles and far less additional shading. So if we knew that the triangle we were looking at is foliage, we could just say, don't add any extra additional half rates, and that might have saved half a millisecond. So there's significant potential for speeding this up, particularly on foliage, by not adding that half rate. Other issues, the other problems we had with noise and possible solutions is that the noise wasn't applied everywhere, but we didn't know where it was applied. So if this was written out to another buffer, we could use that to only add additional half rate shading in those areas. As I said, we could disable it on certain materials, or if the camera's moving fast, or do we really need the noise? Another observation is we only needed to add the noise to fix the lighting pass. We didn't actually need the additional shading for the deferred texturing. So it would be possible to run these with different shading rate images and therefore different VRCS buffers and therefore a different number of primary pixels for deferred texturing and deferred lighting. This might introduce a problem with reflections because we have more duplicate G-buffer normals. Something you could do with this is you could run the normal decode and the normal outputs of the G-buffer at thread per pixel as normal, then go into the VRCS prefix, retire a bunch of waves, write the rest of the G-buffers. Something else, games with VRS have typically got extremely good wins whenever post-processing is blurring the hell out of the image. So this is depth of field and motion blur. And unfortunately, on IDTech 8, we couldn't take advantage of that. And the reason is that IDTech 8 overlaps frames, and sometimes we needed the shading rate image before post-processing for the previous frame completed. So the solution here would just be for depth of field in particular, you can do some math in the shader and say, this is going to be blurred later on, let's just reduce the shading rate. So in conclusion, we managed to get the performance back to 1 to 2 milliseconds typically, which is huge for a 60 Hz title. This netted an overall increase in image quality on the consoles. It allowed Series S in particular to hit our frame time and resolution targets. It works on PC also. It does require a reasonable resolution. The higher the resolution, the more of a win you're going to get out of this, and deblocking was essential. We have only scratched the surface. It could be applied to more passes. With ray tracing in particular, that could be a massive saving. Better pixel selection algorithm, better fix for the noise issue, less half rate shading on foliage, and we've easily got another millisecond win here. I don't think there'd be any problem getting another millisecond. And with that is the end of the talk. And I would like to say thank you very much to everybody at IDS for entrusting us to checking code and probably not look too hard at it several days before we shipped.